Good, the recording's on, everyone's back. Once again, we won't have a long introduction for Alina, because she's already spoken this week. But I think we're all looking forward to the second part of her talk, which is on eggplants in arithmetic statistics, real functions. Once again, I'd encourage everyone to, I think the channel for Alina's talk in the Zulip is like a really good example of the way this is supposed to work. There's been a lot of discussion there, continuing after the talk, so I'd really encourage all of you to get in there and get involved. Take it away, Alina, if you want to share your screen.
Okay, let's try this amazing feat here. Okay. Are we good? Everybody can see this, yes. Okay, so once again, we are going to go low tech right after the first slide. And I decided to change the title on you people and call it Open Problems in Arithmetic Statistics. So let me remind you the setup from 2 days ago. We are looking at a smooth, projective, geometrically reducible, all that good stuff, curve defined over a finite field. And we're going to call the genus of the curve G, and the field is going to have Q elements in general. So the things that we are interested in was the distribution of the number of points of FQ points on C, the rational points. And the other thing that we are very interested in, which is this, really the subject of a large part of Sarah's book, is this the supremum of the number of points taken by the curves of genus G, which we call NQ of G. And I'm going to organize today's talk very much like the way I organized the talk on Tuesday. Namely, I'm going to look in 3 directions: the geometric direction, the probabilistic direction, and the arithmetic direction. So the geometric one is the one where one fixes the genus G and lets the number of elements in the finite field go to infinity. The probabilistic point of view is the sort of polar opposite of this, where you fix the finite field and you let the genus of the curves go to infinity. And then there is the arithmetic world, in which we are looking at a curve may be defined over Q, may be defined over a number field, and then we reduce modulo the finite places and let the norm of those finite places go to infinity. Okay, so those are the 3 things. And after this, it's all going to be written in real time. So let me start with the geometric world, just right, because there is, first of all, this is how I started on Tuesday, but more importantly, there was some discussion in this geometric direction in the Zulip that I found very inspiring, and also discussion after the talk. So, right, so let's, one of the things that we were looking at was this NQ of G, say, for Q much larger than G. So let's take a little bit of a step back and see what we can say about this. So if you look at the number of points on a curve of genus G over FQ, and you look at sort of how far it is from Q plus 1, then the wave bound gives you 2G square root of Q. So this is different situation than the Drimfeld-Laduz one, which is the large genus G situation. Here we have this one. And of course, so right, if you really spell this out, what it tells you is that, right, this is between Q, the number of points is between this guy. It decided that I must want to draw something. And this guy. Now, if Q is much, so like it depends how you look at this. So maybe I actually don't necessarily want to make Q much smaller, much bigger than G. So what I really want, I kind of want to actually do right now somehow a little different. So the Katz and Sarnak philosophy tells me what happens when I fix G and I let Q become large, and basically it tells me that it gives me that distribution that's given by random matrices. And the question that Christophe was asking was what happens to NQ of G? And he made this comment that it's really a lower order term in the distribution. So Katz-Sarnak gives you the main term in the distribution. It gives you an asymptotic for, you know, the number of these guys, C of genus G, sort of, let's say for G less than X or something, and then it gives you a main term. But the question is, what happens when you when the genus is big enough? If it's you can see how like you can arrange that Q plus 1 minus 2G times square root of Q is actually negative. So already you lose the end range on the left of your distribution. And then, of course, you can also lose the sort of what Christophe's question is, what happens about the right end of this range? So what happens to the maximum? Like how, you know, where do we really stop? Because we don't really get to Q plus necessarily to Q plus 1 plus 2G square root of Q. So this, you have a main term, but you also have maybe some lower order terms in here. And as Christophe was saying, what his question is really about a lower order term. And so this is, of course, a question that we know very little about, but one situation that we can sort of take some inspiration from maybe is the idea of moments of L functions. So what do I mean by that? Well, so let's take a quick tour in a different part of the of number theory, and let's look at this distribution. We are going to take, let's say that we are over Q, and we are going to look at chi d, the quadratic character of conductor D. And then you have an L function, and you're looking at this L f chi d as D increases. And what you would like to say is that this sort of grows like D to the epsilon as D increases. So this would be, this is called the Lindelof conjecture. We cannot get anywhere close to this, of course, but what we can do is look at things like this. And so in other words, moments. And the interesting thing about this is that we, like what Katz-Sarnak predicts is the main term in these moments. And somehow the random matrix theory point of view doesn't really give you the lower order terms, but there are other methods that do. So an example would be the fourth moment here. Well, I should have put just K, not just necessarily to K. So if you look at these guys, you have some, this is supposed to grow like some constant times X times a polynomial of degree 10 in log X, and that's the main term. And then somehow the random matrix theory cannot really tell you anything about the lower order terms. There is another method that predicts these moments that's called the multiple Dirichlet series that gives you here a term of order x to the 3/4. Plus, then you're going to have like the name of the game is to get all the way to a half plus epsilon. So this was somehow a difference in the predictions that came from random matrix theory. Like random matrix theory can give you this thing over here, but this dude was came out of the multiple Dirichlet series, and people were very curious to see which one was really really correct. And there were a few years ago, Mike Rubinstein did some computations, and he said that he can start to see some accumulation around x to the 3/4. So it seems that this method might see some lower order terms. So I'm not sure exactly how one would compute moments to get NQ of G out of that, like, you know, how you compute moments of the distribution of the number of points over FQ, but that's something that we should try to, like, that's one possible way of attacking this. If you want lower order terms, go to moments. That's basically probability for you. That's how it goes. Okay, so then I have no idea what would go into it and how you know, how far we are from being able to say anything like this, because it only occurred to me like yesterday, so no idea that you could do this. But of course, so I should say that in this geometric situation, the biggest problem that we have is, so sort of big problem is to try to, so to speak, port results from function fields to number fields. So all, like, we somehow, right, Katz-Sarnak uses this et al. Cohomology point of view to give you, to make the connection with random matrices, and over number fields, we have nothing like et al. Cohomology to give us anything. So, but there is still this super strong analogy between, you know, number fields and function fields, right? Where, like, that all of you know, so I'm not going to insist on it. And the big problem here is, how can you find something in all these results that don't necessarily use directly et al. Cohomology that you can port back to number fields? Any of those methods, can you make them work? So you can prove some of these results. Over number fields, we, right, the best we can do typically is to run a bunch of computations and say, oh, look, it looks very much like the distribution predicted by the random matrix theory. But proving that stuff is much harder, and we don't have a method to do it systematically. Okay, so that's somehow the stuff that I wanted to say about the geometric situation. But if anybody has any question, comments, additions right now, do let me know. I'm gonna pause for a sec, because they are gonna move to the probabilistic world after this.
Yeah, I do have a question. Actually, I just asked Christoph and he didn't know, so I'm asking everybody now. So, I mean, there is this paper that we discussed 2 days ago by Christoph, and actually also by Ben, I think that is one of the authors, in which we get these skew distributions. And I was wondering if this term of x to the 3/4 somehow explain this skew.
I would love to know the answer to that question. That's a very good question, and I would love to know the answer. As I said, I haven't had time to really think this through. It was just sort of like, that's the only method that I know this at the moment to try to get you anything of lower order in this world. There are other methods in other worlds, like the, you know, the secondary term inside the Davenport-Heilbronn formula and stuff like that over number fields, but this thing with L functions, that's the only thing that I know of. The moments is the only thing.
I mean, this term is very nice, so we have to take it.
Yeah.
But the funny thing is also that what we obtain, I mean, of course, it doesn't work when Q gets big, but when Q was small,
Yeah.
I mean, then, I mean, you could see that you don't need anything. I mean, it's just the Bernoulli distribution, which is not that symmetric.
Mm-hmm. Yeah.
And so it's a bit weird, but of course, I mean, it works when you have like,
Okay.
I mean, the genus is small compared to, compared to Q, or Q is small compared to G.
Yeah. Okay. So probabilistic situation in the probabilistic world. This is so here we have, right, in the thing that one would like to get in general, of course, is sort of for G in sort of maybe SN transitive subgroup. In general, you would want to know sort of the G statistics in general, in the sense that, right, so G statistics, by that I mean, right, number of points on some curve C, where you have C is a G cover of P1. So you have, it's a cover and you have a fiber and G acts on the fibers. So, right, like hyperelliptic curves are the example where G is Z mod 2. And in general, this is somehow the big thing that we would like to have. This is very analogous to computing, computing the distribution of, you know, number fields of discriminant up to X with a given Galois group. That would be so this brings us to, right, essentially Malle's conjecture. In function fields. And the great thing about it is that, right, so Malle's conjecture, as I was reading just this morning on Jordan Ellenberg's blog, is a great conjecture. It has this, the tiny defect that it's false in some cases. So, but this at least has been fixed by, so Turkelli gave I think it's 2008. He gave a formulation for this. So this is, he formulated Malle over FQ of T. And he takes into account, he has to do this twisting of Hurwitz spaces, and he gets a very complicated statement, but it has the advantage that it has, as particular cases, both the Malle's conjecture in the situations where we know it holds, and in the cases where they found these counterexamples to it, it actually gets those counterexamples. It accounts for them. Now, of course, Malle's conjecture is not really counting the number of points over FQ, is just enumerating the curves. That would be the equivalent, because you're just looking for how, but even that is hard. So anything like, you know, proving this over function fields would be great. And in general, right, so there is some hope in the sense that, right, there is, so there are a couple of ideas in this direction. One is to look at Wright's paper on abelian number fields or abelian extensions, where he essentially proves Malle's conjecture when G is abelian in 1989. And that we might have a hope of doing, because there are all these these things that have been done. So as I mentioned, we have done Z mod LZ, and then right, the work of Elisa and Meleleo and Milione, they do this biquadratic stuff. So in general, and there are other papers like this where you can take products. So and then in Melanie's wood about S3 covers of P1, she mentions that in general, she expects her method to work for Z mod L and Z. So if you can combine sort of this, the technique that gave you product with this technique about Z mod L and Z, then you can basically, that should give you something for all finite abelian groups, at least. So that is something that we can try to do. And of course, we are not somehow in this world, we are not done, because that just gives us a way of parameterizing the curves. So now we have to look at like the number of points over FQ of them to, for us to in our world. But there is a hope of actually trying to do this, combining these methods. And then of course, there is like the fact, and then in general, if you're dealing with a non-abelian group, then we know very little. Melanie Wood did this for S3. I think it was in 2012, I want to say. And we know precious little beyond this. There is some stuff done for D4, and as far as I can tell, Ila Varma is involved in all of them. So because this is somehow small enough, and you can try to say something. But there should be one hopes that if one takes a small enough group that we understand really really well, one could try to do this statistics for G covers of P1. So that would be, of course, this takes you into this world of non-abelian Cohen-Lenstra that people have been working in, right? This is a subject that was started by Melanie Wood, and then I don't remember if it's already on the archive, but I know that Melanie and Robert Lemke Oliver and Julia Wang have an upcoming paper about this problem, where they sort of go in. They can somehow, if they know the Cohen-Lenstra, if they can prove the Cohen-Lenstra heuristic for some smaller groups, they can sort of go up in towers. So that would be super exciting when that comes up. You can also do something where, right, so if you're looking at something that's defined like a curve defined over FQ, right, so if you look at the number of points over FQ, the typical result in this is that you have a sum of Q plus 1 random variables that give you this, the distribution of this number of points. But it would be interesting to sort of look at, I can take the same curve, the same curves as before, the ones that are defined over FQ, and look at the FQ points and FQ to the N and so on points. So somehow do a double limit in Q and G, where, so this would be double limit in Q and G. If you just, so, but of course is somehow your first taking the limit over G, and then you're looking as Q increases, but you're looking only on things defined over FQ. If you're doing a pure double limit, then there is a result that tells you that it's a Gaussian, and it essentially, that can be proven again with moments. There is a way of taking the limit, right, taking the Katz-Sarnak, which is already the limit in large Q, and then taking the limit over G, and that gives you there is a paper of Percy Diakonis and I think Shashahani, that tells you that in that case you get a Gaussian. But this thing is just about like a bunch of conditions. So you have this random matrices, sure, but then you cut this. You have these conditions, right? That the trace of that random matrix better be an integer, and then that when you look at the next level where you look at over FQ squared, you get another bunch of random matrices, but again, you have some conditions that are very much in integers. So what kind of space do these conditions cut out of the space of random matrices that you're looking at is an interesting question. So this would be like sort of a joint distribution for all these guys. What can you say about that? So this is something that I would very much like to know the answer for, because we don't even have a heuristic model for what one should get at the end of this process. Okay, and I'm going to stop there for the probabilistic situation and move on to the arithmetic world, which is somehow, well, my favorite these days. Let's put it this way. And right, one can find quite a few problems, some of them in Zulip. So let me start with sort of the big problem.
Can I just ask Alina for on the previous slide?
Yeah.
I mean, because you said you don't even have an idea, but if you would do it like for a plane curve, I mean, then, I mean, as you did a bit like for the cardinality of CFQ, you could have a formula for the cardinality of CFQ square as a sum of random variables. So you should get the joint distribution, or is it completely trivial?
I haven't actually tried to think about it that way, right? So the thing is, at this point, you have to like sort of recover here, and then you have sort of, you know, Q squared plus 1, so to speak, over here. So you have these other guys, and then, but of course, this dudes contribute actually is like you're squaring them. So this is something that could when you're looking at this, there is this paper by Brock and Granville that talk about this bias when the power when you have FQ squared and FQ to the fourth and so on, that comes into play, and it comes from the fact that you're squaring these variables. So in here, in x1 through xq plus 1, the 1s and -1 are distributed equally. They have 50-50 chance of being +1 versus -1, minus the little bit that zeros can occur, so to speak. I'm thinking of them of like the right. You have 1 point, and then is the deviation from 1 point, right? So the zeros and the 2 are equally distributed, and the 1 is really tiny. And but these guys, when you go to FQ squared, the things that were +1 and -1 before, the difference between the number of points in the fiber and 1, those get squared. So that explains that Brock and Granville bias that they noticed, that they proved. So if you're looking at plane curves, maybe you can say more, and it's easier, but I don't know, maybe you're right and it's completely trivial, and then we have at least one model for one family. That would be great. I haven't really thought about what happens in that case. I was just thinking of this, like the thing that I had in mind were the hyperelliptics when I tried to do this, and I couldn't. That's the model there is non-trivial at all.
Thanks.
So maybe for playing, I like someone in this audience should think about plane curves. But that's great. Somebody record that in Zulip, please. So we have it. Okay, so let me go back to the arithmetic situation. And the big problem that we have right now is to prove Sato-Tate for a billion surfaces. So what's the issue here? We have the equidistribution theorem of Serre that tells us that we need to look at the meromorphic continuation plus analytic properties of sort of being non-zero on the line at the right of the critical strip, except non-zero, no zeros and no poles, except possibly at s equal 1 and so on, for all non-trivial irreducible representations of SP4. And here the problem is that there are it's an infinite sequence, and even doing the standard representation is a really hard problem. This is actually the paramodular conjecture. So, you know, we'd be lucky to get a second one, not to mention infinitely many. So we need some new ideas here on how to attack this problem for this infinite sequence of L functions. So that's what's that is somehow the next frontier in the Sato-Tate game. But okay, since we are on the topic of Sato-Tate, let me sort of talk about our problems. Right, so you have in general the Sato-Tate is formulated for a billion varieties of dimension d, and you know what, like one computes this, and I would be really curious to know, right? So you have this a billion varieties of, say, dimension g, and in here you have Jacobians of curves of genus G. And the question that I would like to know the answer to, I'm super curious about, is, are the Sato-Tate distributions the same, or do they differ? In other words, does this condition of being a Jacobian cut uniformly across the distribution, or do you have different things? So, right, this for D1, 2, and 3, this is the kind of thing that well, at least for 1 and 2, I think this for 1 is really there is no problem, because a billion varieties of dimension 1 and Jacobian of curves of genus 1. So, for genus 2, I think this is answered in Fité, Kedlaya, Roger, and Sutherland. For dimension 3, I think the thing that Fité, Kedlaya, and Sutherland look at is a billion threefolds. But of course, the higher the genus, the bigger the discrepancy between the space of a billion varieties of that dimension and the subspace of Jacobians inside it. So I would be super curious to find this out. And of course, speaking of that, sort of, can you find all the Sato-Tate groups of a billion varieties of dimension D, right? For 1, 2, and 3, sure, but remember, it gets progressively harder. We have 3 options in dimension 1, we have 52 options in dimension 2, and 410 in dimension 3. So D bigger than 4. Oops, shoot, I keep writing at the bottom of the page. And you guys cannot see that. So that's another interesting interesting problem. And of course, one expects that one can prove some cases of it, especially the non-generic case, using some automorphic form techniques, because in general the L functions you have to deal with are easier to control. Another problem that I really wanna mention is so the question, so it's known since like 1975 by a paper of Madan and Pal that there are infinitely many simple abelian varieties over F2 with exactly one F2 rational point. So the question is, well, replace this by 2. Can we say anything like this? Because the techniques that that Madan and Pal use, it's just something about algebraic numbers, and whose conjugates are all in a certain region of the complex plane. But that tells you absolutely nothing about 2 F2 rational points. That method just does not apply, and I have no idea how to approach this. And I guess the last I left for last a question that I know Ser himself is interested in, which is the question of ordinary primes. Namely, for an abelian variety, right? So for an abelian variety, say X, defined over Q, you reduce mod P. And the question is, prove that there are infinitely many P's for which this reduction, I'm gonna abuse notation, is ordinary. And of course, if you manage to do that, so that would be, I guess this is sort of a, maybe it's a conjecture or something, but then if you manage to do that, basically is what's the density? Of these ordinary primes. So we don't even have a guess in general for this. Right, and so this would be an this is again a super interesting question about ordinary reduction, and we don't I have no idea how to sort of approach this. I don't think Sato Tate actually tells you anything about it, but maybe I'm wrong. And I guess maybe I should say, as I forget who pointed out in Zulip, there is a paper by, a set of notes by Nick Katz, Simple Things We Do Not Know, that has a bunch of problems in this direction. Like, for instance, prove that, like Sato Tate would you would think that if you look at the number of elliptic curves with positive AP versus negative AP, that should be 50-50, but we have no idea how to do that. Okay, so I will stop here because I am way over time.
So there's a lot of virtual clapping and some real clapping, and even some people clapping on mute. So thanks for really a nice talk. Does anyone have any more questions that they'd like to jump in for? I think if we've definitely got a few minutes of scheduled time left. Of course, we can stick around beyond that. But if anyone has any questions, there's still some time, or comments, or.
Oh well, yes, I have a question. So there's this quantity that we call the defect, the difference between these quantities that appear in the talk of G and G times the integral part of Q. And in the interview to Sarah, it's mentioned that this problem of whether this defect is
Francesc, I am sorry. Ben, I think the echo is coming from you, and I am so sorry, but I'm going to ask you to maybe mute while.
I'll take the headphone.
Or maybe it's Francesc. Ooh. Because I couldn't really hear what you were saying. I think it was Francesc. I am so sorry. I apologize. Yeah.
Is now better?
Yes, I think it was you.
Okay, yes, sorry. So, I wanted to ask about this problem that asks whether the defect is O of 1 when Q varies and for a fixed G. And okay, maybe this is a very difficult question, but I'd like to know what's the best upper bound for the defect that we know. Is it known that it's
Sorry, that's a question for Christopher.
Q to the epsilon or log Q or?
I think, I mean, there is this result. I mean, Everett maybe can jump in. I mean, the lim inf.
You throw the question to other people.
Hey, delegate. It's a very important skill.
No, I think.
Yeah, the bounds on the lim inf for non-square prime powers is pretty bad. That's what I remember off the top of my head.
Yeah, sorry, I can't help neither. I mean, but yeah, there is a result, but as Everett says, maybe it's really bad for prime powers, or yeah, okay, or for FP.
Right, for non-square fields.
But Francesc, I mean, I still have to read your answer in the Zulip, Alina, because for me it was a bit amazing that, I mean, one can deduce what Francesc wrote from the Satotate, but yeah, I still have to read about it, and I was also very surprised about this argument. I mean, that I wrote about this Q to the G square over 8.
Yeah.
Because I mean, I didn't realize, and indeed, I mean, the fact that it's a G square, I mean, exponents that compensate everything and that make you think at the end that, yes, I mean, probably Sarah is right to be optimistic, and one should think that, I mean, the defect is O1, yeah. But then, I mean, it makes also, I mean, it made also that I changed my mind completely on even the case of genus 3, because I thought that maybe we could prove that there is something of defect greater than 3. But now I'm thinking the contrary, because there are so many possible cases of abelian variety, which are e to the cube or with e of defect 0 or e of defect 1, that, yeah, probably, I mean, as it is to toss a coin each time for the Serre obstruction, there is no reason not to have a Jacobian inside this large set. So, but of course, everything depends on these super hard things about like believing or not that I mean, Jacobians distributes well among abelian varieties somehow. And I don't know, I mean, if people can have a hope, I mean, with techniques that come from, I don't know, this, I'm just Teichmüller spaces and all what Zimmermann does. I don't know, I mean, if it can help or not. I mean, what's your intuition, Alina?
I don't actually know. I think that somehow, right? So what Katz-Sarnak sort of seems to suggest is that if you fix the genus and you let Q go to infinity, whatever happens to that defect, it has to be way smaller order, right, than the main term, because otherwise they would be able to see it.
Mm-hmm.
It would affect what they see. So somehow what Katz-Sarnak seems to say, or at least my interpretation of it in terms of this defect, is that the defect sort of disappears if you take this limit. So it has to be it has to be something of as you said, a lower order term in there. Which of these techniques can tell you something? I don't know, but I really liked that both arguments, the one that Francesc wrote and the one that you wrote in Zulip, are super striking. I still need to process because, you know, I was asleep while you were guys having this discussion. So I will withhold any ruling on it. I have no idea. I would love to understand. I would love to understand that more. Defect is not something that I really thought in depth about before until this conference and reading Serre's book. And on a different topic, actually, right, the question of ordinary primes that is still apparently on our screens. I want to thank Drew Sutherland for the citation that he put in Zulip. I hadn't realized that somebody had done anything about it, but there is this paper by Will Savin from 2015 that Drew pointed to, and he proves that for the set of ordinary primes for an abelian surface, it's 1/1/2 or 1/4 depending on the Ladrig monodromy group. Oh, sorry, it was J factor. I'm so sorry. I credited the wrong person about Zulip. Apologies, Jeff. my Zulip has gotten super active all of a sudden. Drew posted the cats paper and this Calegari. Something that Calegari wrote in Motives on L functions, but I have to look at as well.
So up to dimension 2, it is solved.
Yes, excellent. We made a great start in this conference. Now somebody do dimension 3 by tomorrow.
I remember also vaguely a paper from Gonzalez and Bayer about like the similar problem of P rank for, but for how can I say, for modular curves.
Mm-hmm.
I mean, when you reduce them over modulo P and trying to find what would be the distribution of this.
And I actually did have, like, the reason why I keep crediting Drew with this is because I actually want to ask him a question. So Francesc mentioned that if you compute, say, for abelian surfaces, you compute the LP polynomials mod P, that's a much faster algorithm than actually computing them for real. And the question that I have is, can you read in any instance the actual Sato-Tate group from this LP mod P? polynomials if you compute that distribution, the distribution of those coefficients.
Yeah, I mean, in some cases, certainly, well, in genus 2, where it's kind of cheating, yes, quite often. I mean, what you're getting, I mean, you know that it's telling you the trace distribution on the nodes, and it's telling you a 2 mod p, which it's telling you the number of times it takes an exact integer value after normalization, and in some cases that will uniquely determine the Sauté group with, if you combine that with the A1 distribution. I'd have to check in dimension 3 though whether there are any cases, but it definitely gives you information. And Francesc has, I know, thought more about this than I have as to whether you can actually give a meaning to those numbers. There's definitely something there. I don't know if Francesc wants to say more. We struggled to try and formulate a conjecture and didn't really nail it down, I don't think.
Oh yeah, no, I don't know.
Yeah, right. I mean, what's hard there is that you're squishing this distribution that was on something of size, an interval of size, what, 12 or so, to something of size 2 or 1 or whatever it is. It's unclear how it folds onto that when you do it. So I don't even, like, as Francesc and I were discussing sort of offline earlier, I don't even know if I would expect the moments to be integers necessarily, because I just don't know what happens, right? It's not an arithmetic quantity.
I'm going to just jump in here and say, for those of you that need a break, you should totally feel free to take one between now and the next hour boundary, because we've still got 2 more talks this evening, and it's you know, it's taking a lot of energy for everyone, I think. And so before everyone runs off, maybe we can have another sort of virtual clap, and then on mute if you like, or using the clapping icon. Those of you who want to keep discussing, it's great. And for everyone else, we'll see you again in 7 or 8 minutes.
Thank you to everybody who contributed to the discussion, by the way, and please continue to post in Zulip.